Welcome again, folks. This is lecture number 17, and today we are going to learn about the flip-flops, but we're going to start off with the SR latch using NAND gate. Previously we had done it using NOR gate. I want to start with this because this is going to be the basic and actually going to set the platform for the flip-flops that we are going to learn today, because they are entirely based on SR latch using the NAND gate. So before we get started, let's look at the property of the NAND gate. So we have NAND gate, say you have inputs X and Y, and then you have the output Z. So you got four possible combinations, 0, 0, 0, 1. Then you have 1, 0, and then 1, 1. And for the NAND gate, we know that the outputs are going to be 1, 1, 1, 0. When both the inputs are high, the output is going to be 0. When any of the inputs is 0, the output is going to be high. Basically, it's an opposite of AND gate. Okay. All right. So we're going to start off, and again, we have this SR latch using the NAND gate. The output of this NAND gate is fed back into the input of this NAND gate. We got Q and Q naught. We know that those are going to be the complement of each other. Let's start with this combination first. When S1 and R1 both are set to 0, 0. So if S1 is 0, R1 is 0. We know when any of the inputs is 0, the output is going to be high. When any of the input is 0, the output is going to be high, which would mean that Q is going to be 1 and Q naught is going to be 1, okay, which is not possible. Okay, we call this invalid, and this is we also refer to as forbidden state. Okay, when we have S1 is equals to 0 and R1 equals to 1. So we got 0 here and we got 1 here. We know when any of the input is 0, the output is going to be 1. So which means this is going to be 1. This one is fed into the input of this NAND gate. 1 and 1 going into NAND gate. 1 and 1 gets you 0. 1 and 1 gets you 0. Okay. So this will be 0 here. So when S1 is 0, R1 is 1, Q is going to be 1, and Q naught is going to be 0. Okay, and we are going to call this condition as set condition, like we previously have done. Let's change the logic a bit here now. S1 is 1, R1 is 0. Okay. S1 is 1, R1 is 0. We know any of the inputs is 0, output is going to be high. This one is fed into this NAND gate input. 1, 1 makes 0. 1, 1 makes 0. So 1, 1 makes 0. So your Q is 0 and Q naught is 1. We call this condition as reset. Okay. Okay, all right, let's try the last combination when both inputs are high. So we got 1 here and we got 1 here. The last input, the last state for the Q was 0, and for the Q naught it was 1. So Q, which was 0, is fed into this NAND gate. 1, 0, 1, 0 gets you 1. Okay, and this 1 is actually then fed into this NAND gate, and 1 and 1 gets you 0, because 1 and when both inputs are high, output is 0. Okay, so if you remember, if you actually recall, for the previous state, when S was 1, R was 0, R1 was 0, we got 0 and 1, and now that we have changed the inputs, both S1 and R1 are set to high, the output didn't change, it remains 0, and Q0 remained 1. Okay, so 0 here, 1 here, there's no change, which means this is acting as a memory. Okay, so this is our basic SR latch using NAND gate, and based on this we are going to create our flip-flops. The schematic of our SR flip-flop. This is basically this part right here. We just did this part right here, the SR latch. Okay, this is the SR latch that we just did. This is supposed to be R1. Okay, you got S1 here, R1 here, and this, because it's a flip-flop, so it needs to be clock triggered, so we have a clock here. Okay, the easiest way to do this would be to actually drive an expression for S1 and R1. So if you look at S1 right here, it's the output of this NAND gate, and the inputs are S and clock, S dot CLK, and then you will have bar on the whole thing. Okay, similarly R1, which is the output of this NAND gate, if you look at the inputs are clock and R, so R dot clock and bar on the whole thing, because it's a NAND gate, it's an opposite of AND gate. Now if you like, you can actually apply De Morgan's here, and then you will get what? You will get S bar plus clock bar, and then you get here R bar plus clock bar. Okay, now again we're gonna have cases here, and we'll have 5 of those cases, 4 of them with clock set to high and 1 of them with clock set to 0. So in case 1, when you have clock set to 0, which means this clock is 0, and this is something that you're gonna have to remember whenever, let it be any kind of flip-flop, whether it's SR, T flip-flop, JK flip-flop, or D flip-flop, whenever clock is 0, the output is going to retain its previous input. So if the previous input was 0, it's gonna retain 0, and Q bar has to be 1, because it has to be a complement of Q. Okay, so at this point we really don't care what is S and R. Okay, when clock is 0, what is going to be S1 and R1? Well, we know any of the input is 0. Going into a NAND gate, the output is going to be 1. Okay, so S1 is 1, R1 is going to be 1, S1 is going to be 1, R1 is going to be 1. So here we don't care about S and R, whether it's 0 and 1. The S1 and R1 are going to be 1. And we know when, let's go back to the previous slide right here. And we know when S1 and R1 were high, when S1 and R1 were high, the output was the previous state, 0, 1. Okay, so we would say, because we don't know what is the previous state, so I'll just write down as memory here. Memory, no change. This is our first case. Okay, let's move on to our second case, which is right here. When clock is high, S is 0, R is 0. Clock is high, S is 0, R is 0. Okay, so if you want, you can actually put these values here. So say S1, this is for case 2. This is for case 2. Okay, in case 2 we got S0, R0, and clock is high. Okay, so S1 is equals to S is 0, So the invert of 0 would be 1 plus clock. Clock is 1, so the invert of 1 would be 0. And you know 1 plus 0 makes 1 because it's an OR gate. Any of the input is high, output is high. So S1 is 1, so we get 1 here. Okay. Now we're going to do R1. So let's put the values for S and R and clock in this equation right here. R is 0, so the invert of 0 would be 1. Clock is 1, so invert of 1 would be 0. And so 1 plus 0 would make 1. So we get 1 here also. And we know when S1 and R1 are high, again from the previous circuit, we just did it. When both inputs are high, S1 and R1, it's a memory, no change. So again, I'll just write it down as memory, no change. Okay, all right. Similarly, I'll do it for another case, which is case number 3, okay, which is right here. S equals to 0 here, R is equals to 1, and again clock is high. Okay, S is 0, so invert of 0 would be 1, so S1 is equals to 1. Clock is high, so invert of that would be 0, so you get 1. R1, again R is 1, so invert of that would be 0. Clock is high, invert of that would be 0. 0 plus 0 gets you 0, so S1 is going to be 1, and R1 is going to be S1 is going to be 1, and R1 is going to be 0. So this is the situation that we have S1 1, R1 0. Okay, now let's look at the truth table from the previous example, because this part is actually the SR latch that we just did. When S1 is 1, R1 is 0. When S1 is 1, R1 is 0. Q is 0, and Q bar is 1. Okay, all right. Again, this is the reset condition. Okay, moving on to case number 4 now. When S is 1 and R is 0. Okay, so this is case 4. S equals to 1, so S1 would be, because S is 1, so invert of that would be 0. Clock is high, so invert of that would be 0. 0 plus 0 equals to 0. R1 is R bar plus clock bar. R is 0, so invert of that would be 1. Clock is 1, invert of that would be 0, so we get 1 here. So S1 is 0, R1 is 1. Okay, let's look at the truth table from the previous example. When S is 1, R1 is 0. S1 is 1. Sorry, S1 is 0 and R1 is 1. S1 is 0, R1 is 1. Q is 1, Q naught is 0. Q is 1, Q naught is 0. This is what we know as set condition. Okay. Similarly, the last case that we have, which is case number 5, which is this right here. Here we have both S and R set to high, and clock is high. So S is high, clock is high, so invert of that would be 0 plus 0, so we get 0 here. R1 is going to be R bar plus clock bar. R is 1, so that would be 0. Clock is 1, invert of that would be 0, so we get 0. So we actually get 0 and 0 here. Okay, S1 is 0, R1 is 0. Let's look at the truth table from the previous example. When S1 is 0, R1 is 0. Q and Q naught were 1, 1. and we know that this is the forbidden state. This cannot happen. Q and Q naught have to be complement of each other. So this is the forbidden state. Okay, so this is actually the truth table for the SR flip-flop. Okay, moving on to the next sheet that we have. There are two new things that we need to learn here. First of all, whenever I use the term QN, N in subscript, that means that's the present state. Remember, we are moving into sequential circuits, and one of the major difference between the combinational logic circuits and the sequential circuits is that in sequential circuit, the output does not only depends upon the input, but it also depends upon the past history of the outputs. Okay, so it's important for us to know what is the present state and what is the next state. So the variable I'm going to use for present state is Qn, and for the next state it's going to be Q and N plus 1 in the subscript. Okay, there are two kind of tables that we are going to do. One is the state table, or also known as a characteristic table. This table shows what would be the next state based on the previous present state and the other inputs. Okay, so if you look at it over here, this is your state characteristic table. In a state and characteristic table, your inputs are going to be the present state and the inputs also, which are S and R in this case, in an SR flip-flop. If you were doing JK flip-flop, it would be present state QN and J and K. Okay, and the output is the next state. Okay, and then we have the excitation table. The excitation table shows the minimum inputs that are necessary to generate a next state or output. In other words, data is rearranged such that the Qn and Qn plus 1 are next to each other on the left, and the inputs are on the right side of the table. And when we do that, I'll show you how we get that done. Okay, so this table, truth table, we just did that. I'll just copy all the values into this table right here real quick. This is the truth table that we have. We started with clock 0, doesn't matter what S and R are. Qn plus 1 is actually going to be no change memory. So whatever is in the state, which is the present state or the previous state. So I'll just write it down as Qn here. Okay, remember this is your memory. Okay, and then we have 0, 0, 0, 1, 1, 0, and 1, 1. When S0, R0, when S0, R0, Q was again memory. So I got Qn here. Remember, this thing is yours. Q next state, Qn plus 1. Okay. Now S0, R1, S0, R1, Q is 0, Q naught is 1. So Qn plus 1 is going to be 0 here. When S is 1, R is 0. S is 1, R is 0, Q is 1. And when S and R both high, S and R both high, Q is actually 1, 1. That's a forbidden state. So we just don't care about it. I'll just write it down as forbidden state here. Okay, once we have the truth table, folks, using the truth table, we can actually derive the state table or the characteristic table. Remember, in the characteristic table, you're going to have your present inputs or previous inputs right next to your inputs. So these are the inputs right here. Okay, this is a previous state or present state, and these are the inputs. And for excuse me, for 3 inputs, we have 8 possible combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Okay, now we're going to have to look at this table, and then using the truth table, we are going to finish this, complete this next state column. Okay, remember this is your next state. Okay, if S is 0, R is 0. Okay, and we're gonna assume that clock is high at all times here. Okay, if S is 0, R is 0. If S is 0, R is 0, Qn plus 1 is Qn. And since Qn is 0, so that will mean Qn plus 1 is going to be 0. Okay, S is 0, R is 1. S is 0, R is 1. The next state is going to be 0. S is 1, R is 0. S is 1, R is 0. Next state is going to be 1. Okay, S1, R1. The next state is going to be the forbidden state. So we just use the don't care here. 0, 0, 0, 0, present state. The next state is actually the present state, and because present state is 1 here, so we get 1 here, 0 here, 1 here, 0 here, 1 here, output is 0, 1 here, 0 here, 1 here, 0 here, next state is 1, and then 1, 1, that's another don't care here, so I'll just write don't care here. Okay, so we have actually finished our state table here. Now with the help of the state table, we are now going to drive the excitation table. The excitation table is a very important, because then it also makes easy for us to come up with a very log code for SR flip-flop. Okay, all right. Before we move on to the excitation table, I just want to quickly finish my K map and get an expression for Qn plus 1. Okay, so our most significant bit Qn here, and then we got S and R here. Remember, you got 0 here, 1, 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so this is 0, 1, 2, 3, 4, 5, 6, and 7. I'm going to look for the minterms. I got 1 here, got don't care here, 4 is 1, 6 is 1, and 7 is don't care. Okay, I'm going to make a card here, and then also I'm going to make another pair here, 6 and 4. Okay, and come up with an expression for Qn plus 1, which is going to be, for the expression for this card would be, the common is 1 here, which is S plus, and then for this pair you got Qn here, Qn bar, so you got Qn, and the common here is 0, 0, which is R bar. Okay, so this is the logic expression to get the next state. Say S is 0, R is 0, because it's a complement, so it needs to be 1, and Qn is 1. Say the previous state is 1. Okay, so 1.1 makes what? 1.1 makes 1 because an AND gate, plus here, and then 0. 0 plus 1 makes 1. Okay, so the next state is going to be 1, and you can actually see that over here also. S was 0, R 0, and then Qn was 1, Qn was 1, you get 1, and that's what you got 1 here. Okay, so you can actually verify, with this equation you can verify this this table, something that we have already done many times in the past. Okay, all right. Excitation table. In an excitation table, you actually put your present state and next state right next to each other. So this is your present state or previous state, and this is your next state. These two go right next to each other, and then followed by the inputs. The inputs is S and R. Okay. Again, we're going to assume that clock, which is also an input, is going to be 1 at all times. Okay, all right. Now, using the state table, characteristic table, we are going to drive the excitation table. So we look at Qn and Qn plus 1. So in other words, we actually look at this column and this column right here. When Qn plus 1 is 0, 0. So there's one instance when Qn and Qn plus 1, 0 is there is another instance where Qn is 0, Qn plus 1 is 0. So what are the S and R? Well, S is 0 at both occasions, so S is going to be 0. R is 0 and 1, so we'll say don't care. So it could be 0, 0 or 0, 1. Okay. Similarly, we're going to do it for the others. When Qn is 0, Qn plus 1 is 1. When Qn is 0, Qn plus 1 is 1. Is there any other? No. So S is 1, R is 0. S is 1, R is 0. Now we look for Sn, Qn 1 and Qn plus 1 0. Qn 1, Qn plus 1 0. So we got this right here. Qn1 is 1 and Qn plus 1 is 0. So S is 0, R is 1. S is 0, R is 1. And then the last one, when Qn is 1, Qn plus 1 is 1. Okay, so we have one Q situation here, and then we also have one situation over here when Qn and Qn plus 1 both are 1. So if you look at the S and R inputs, R is 0 in both the cases, so R is going to be 0. S is 0 here and S is 1 here. So this is going to be don't care. So it could be 1, 0 or 0, 0. Okay, so we have now finished the excitation table for the SR flip-flop. We are now going to move on to the next flip-flop, which is going to be the D flip-flop. And so let's start with the schematic. So if you look at, again, this makes the basic SR latch that we started this lecture with. Okay, now remember we had this situation when both inputs were high. S and R were high. S and R were high. We got into a state condition where it was a forbidden state because it was giving us 1, 1, and Q and Q naught cannot be same. So in order to avoid that, we are using an inverter here, which means S and R cannot be same at the same time. Okay, if S is 0, data coming as 0, so S will be 0 and R will be 1 because it's going to an inverter, correct? So therefore, if it's 1, you get 1 here and then you get 0 here. So you have 0, 1 or 1, 0. So we can switch between set and reset. We are able to avoid the forbidden state that we have over here. Okay, so let's move on to, I'll be actually needing the truth table that we have for the SR latch from the first example. Okay, all right, so let's move on. Again, when we have clock 0, I don't care what the input is, the next state is always going to be the previous state or the present state, Qn. So this will be the previous state. When clock is 1 and D is 0, when clock is 1 and D is 0, which means S is going to be what? S is going to be 0. Clock is going to be 1 here. This 0 goes into inverter, becomes 1, and clock is 1 here. Okay, all right. Now let's look at the because we know this part is the SR flip-flop. So if you look at the truth table for the SR flip-flop, when S is 0 and R is 1, when S is 0 and R is 1, S1 is 1, R1 is 0, S1 is 1, R1 is 0, okay, and when S1 is 1 and R1 is 0, Q is 0 and Q naught is 1. Okay, so the present state is actually going to be 0. Okay, makes sense? So this is the next state, which is going to be 0. Okay, clock is 1, D is 1. Okay, clock is 1, D is 1. D being 1 means S is going to be 1. This 1 goes to inverter, becomes 0, so that means R is 0. Clock is high again. Okay, we look at the truth table from the previous example. S is 1, R is 0. S is 1, R is 0. So S1 is going to be 0, R1 is going to be 1. R1 is going to be S1 is going to be 0. And then when S1 is 0, R1 is 1, S1 is 0, R1 is 1, Q is going to be 1, and Q naught is going to be 0. Okay, so your next state is actually Q, which is 1, so you get 1 here. So next state is going to be 1. Now, if you look at this values right here, if you focus on this part, when clock is high, the next state is always equals to D. If the clock is high, D is 0, next state is 0. If clock is high, D is 1, next state is 1. So I can just drive an expression for the next state is always going to be D when clock is high. And we'll see that. Okay, similarly now we are going to complete the characteristic table. And I just told you in a characteristic table you put your inputs and the present inputs, the previous input right next to each other. Here we are actually considering clock in there too. You don't necessarily have to. You can also assume that clock is high at all times, but I'll just put it in here. So 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1. Okay, now this should be fairly simple. We know when clock is 0, the next state is actually going to be whatever the previous state, and because the previous state is 0, so it's going to be 0. So for all the time when the clock is 0, Qn plus 1 is going to be equals to the previous state. So previous state is 1 here, previous state is 0 here, previous state is 1 here. Okay. So 0, 1, 0, 1. I can write it down here also. When clock equals to 0, next state, when clock is 0, next state is equals to present state. Okay. Now clock is 1, D is 0, clock is 1, D is 0, clock is 1, D is 0, next state is 0. Clock is 1, D is 0, the next state is going to be 0. Clock is 1, D is 1, next state is going to be 1. Clock is 1, D is 1, clock is 1, D is 1, next state is going to be 1. Okay, all right. So for this one, clock is equals to 0, and for here, clock is equals to 1 high. Okay, now from here we're gonna move on to our excitation table using the state characteristic table right here. Again, you know, we got our previous state and next states right next to each other in excitation table, and this is our input, which is D. Okay. When Qn is 0, Qn plus 1 is 0. Okay. When Qn is 0, Qn plus 1 is 0. We got two occasions where, and then we got 0, 0 here also. So let's look at D. D is actually don't care here, right? Because D could be 0, D could be 1, so it has to be don't care. So when Qn is 0, Qn plus 1, D could either be 0 or be 1. When Qn is 0, Qn next state is 1. Qn is 0, next state is 1, D is 1. Okay. Q is 1, Qn plus 1 is 0. So 1, 0. So that would be this one right here. So the D is 0. So you get 0 here. Qn 1, Qn plus 1, present state and next state both are high. So we got one instance over here. Then we got one instance over here. And then one instance over here. Let's look at D. D is 0 here, D is 1 here, D is 1 here. So don't care. It could either be 0 or it could be 1. The expression for the next state, which I already have it over here, but let's just make sure we got this right. And again, we got clock here, and then D and Qn, D dot Qn here. So 0, 0, 0, 1. When we're using K-map, getting the expression for next state, we are looking at the state table. This is 1, 1. This is 1, 0, 0, and 1. So 0, 1, 2, 3, 4, 5, 6, 7. Let's look at the min terms. So we got this 1 here. 3 is 1. 6 and 7 are 1. Okay. We will make these two pairs. Okay. We're not going to worry about these hazards at this point. So the expression for this one would be clock bar dot the common here is Qn plus clock dot common here is this one right here, so that's D. Okay, so this is the expression that we have for the next state. Okay, now notice here, if clock is high, and if I put this value here, okay, the complement of 1 would be 0, so this whole term will be 0. This whole term will be 0 plus clock is 1 dot D. Okay, so 0 plus 1 dot D would be basically 1D equals to D. So Qn plus 1 is actually equals to D, and that's what we had. Qn plus 1 equals to D. Okay, whenever the clock is high, the next state is always going to be equal to D. Okay, something that you should remember, and it's also one of the most easiest flip-flop to deal with because the next state equation is very simple. Okay, so we have covered SR flip-flop. Let's get started with JK flip-flop. Now, a JK flip-flop is the most versatile of the basic flip-flops. It has the input following character of the clock D flip-flop, but has two inputs. Traditionally labeled J and K, we use JK flip-flop to overcome the forbidden state. The modified RS circuit that eliminated race condition was named JK in his honor. So if you actually look at the JK flip-flop, previously you had S and R, which are now replaced by J and K, and you have a third input. Notice you have Q, which is feeded into the input of this NAND gate, and then you have this Q naught, which is then feeded into the input of this NAND gate. So that made a little bit of changes to the SR flip-flop, and now that we have JK flip-flop, we should be able to overcome the forbidden state. And so we'll start working on our truth table. So this is our truth table right here. Okay, clock is, and we have like different cases here, correct? Like we have done in the past. So this is case 1, in which clock is 0. And we know when clock is 0, it really doesn't matter what J and K are. Q and Q bar are going to be whatever is in the memory. Okay, so this is acting as a memory here. Okay, so the Qn plus 1 is basically going to be Q of n. Okay, now clock is high, so this is your case 2. Clock is high, J is 0, K is 0. Okay, which means J is 0 here, K is 0, clock is high, so you get 1 here, and you also get 1 here. Now here we are going to assume, because we don't know what the values of Q and Q naught are, we are going to assume, for the sake of completing this table, we're going to assume that Q is 0 and Q naught is 1. Okay, so initially this is 0 and this is 1. So this 1 is feeded into this input right here, so this is going to be 1 here, and then this output is feeded into the input of this NAND gate, so this is 0 here. We know for the NAND gate, so say you have two inputs X and Y, and the output Z, 0 0 0 1 1 0 1 1. So the output is actually 1 when any of the input is 0. When both inputs are high, output is 0. Okay, so 1 0 1 would actually make 1. Okay, 1 0 0, any of the input is 0, output is 1. Now S is 1 and R is 1. So I'm going to actually go back to our truth table for SR flip-flop, which is right here. When S was 1, R1 was 1. It was acting as a memory, so no change. So again, it is acting as a memory, and in the memory, Q is equals to 0. Q bar is equals to 1. Okay, so this is going to be Qn. Okay, again, it's acting as a memory. Okay, now let's move on to the next combination, where you have J equals to 0 and K equals to 1. So this would mean you got 0 here, K is equals to 1, clock is 1, clock is 1. This is 0, Q is feeded here, so this is 0, and Q naught, which is 1, is feeded here. Okay, now we get 1 0 1. Again, this will be 1 going to a NAND gate. Any of the input 0, output is 1. 1 1 0. We're looking at the red, so 1 1 0 gets you 1 also. And again, if S is 1, R is 1, you, this is 1, R is 1, no change. So this will be, again, it will be 0, and this will be 1 right here. okay? And qn plus 1, because qn is basically q, so because it's 0, so this will be 0 here. Now moving on to j being 1 and k being 0. Let me change the color. The reason I have set this to 0 is because even if the previous states were 1 and 0, and you can try that combination, even if the previous states were 1 and 0, you'll still get 0 here, okay? Moving on to j being 1 and k equals to 0, so j is going to be 1 this time, k is going to be 0, clock is 1, so you get 1 here. Now q is 0, q is 0 here, so this is feeded into this thing right here, and q naught is 1, so this is feeded here. So 1 1 1, we're looking at the green, 1 1 1 gets you 0, okay, and then 1 0 0 gets you 1. So when s is 0, r is 1. Let's look at the truth table again. When s is 0, r is 1, q is 1, q naught is 0. So you get 1 here, 0 here, so qn plus 1 would be 1. Okay. Moving on to the last combination, where we have j equals to 1, k equals to 1. Now this is interesting, and I want you to focus here. Okay, now both j and k are 1, so I got 1 here and I got 1 here. Okay, clock is high again, clock is high again. Q previously is 1 now, so this is going to be 1, and q naught is going to be 0, so you get 0 here. So we're looking at black, 0 1 1, that gets you 1, okay, and then 1 1 1, that gets you 0, correct? So when s is 1 and r is 0, when s is 1 and r is 0, we get 0 1, so which means this is going to be 0 and this is going to be 1, okay? Now I want to try this again. I want to try j and k, setting them to 1, and then with this previous states I want to try one more time and see what do I get. This is the unique property of jk, and what's going to happen now is very interesting. Okay, because I got a lot of stuff going in here, so I'm just gonna take a new sheet. Okay, remember we are working on this case right here, so j and k both are set to 1, clock is high, so you get 1 here and you get 1 here. Now what are the previous states, q and q naught? Those are 0 and 1. Okay, so I got 0 here and 1 here. These are fed into the inputs of these NAND gates. So this is 0 and this is 1. We know 111 gets us 0 going through a NAND gate, and 110 gets you 1. Okay. And also let me write it down. Previously we had 0 here and then we had 1 here. So when s is 0, r is 1. What should be q and q naught? Let's look at the truth table again. When s is 0, r is 1. The reason it's defined as S1 and R1 is because in this circuit we had it S1 and R1. Okay, but it's the same thing. Okay, so when S is 0 and R is 1, S is 0, R is 1, we get Q1, Q naught 0. Q1, Q naught 0. Okay, now if you notice here, previously we were getting 0, 1. When the next clock comes in, it actually changed from 0 to 1, and Q naught became 1 to 0 because they have to be complement of each other. Okay, so that's interesting. So there is a complement. There's an effect that we know as toggling going on. Let's try one more combination. Again, keeping J and K set to 1. Okay. Now the previous values are 1 and 0. Clock is always going to be high. And so we're looking at the blue. This one is fed into the input of this NAND gate right here. And this 0 is fed into this input of the NAND gate. Okay, so 0, 1, 1 gets you 1, and then 1, 1, 1 gets you 0. So when S is 1 and R is 0, let's look at the truth table. When S is 1, R is 0, Q is 0, Q naught is 1. Q is 0, Q naught is 1. So if you look at these three, situations where we had J and K set to 1, when the first clock arrived, the Q was 0, Q naught was 1. When the next clock arrived, J and K set, was still 1, but then Q changed from 0 to 1 and Q naught changed from 1 to 0. When the next clock cycle arrived, again J and K were set to 1. 1 changed to 0, 0 changed to 1. So this is what we know as a toggling effect. Okay? It's basically going on and off, on and off, on and off. What does it really mean is, say you have a clock okay, and when J and K are high, when J, K both are set to high 1, what would be your output? Q. Okay, well, when the clock goes high, it's going to toggle for a amount of time. The clock is high. And it's going to keep on doing that. Okay, so this is one clock cycle. This is 2. Okay, for the amount of time the clock is high, it is actually going to toggle between 0 and 1, and that's what it's doing over here. So this is going to be Qn bar on the whole thing. So the next state is going to be the complement of the previous state. If I go back to this sheet right here now, again, so this would mean this would be Qn bar, and this is the toggling effect. Okay. One of the drawback of this toggling effect is because this is uncontrolled toggling. We were not expecting it. We were not doing it intentionally, but it's just happening. There's no control over it that we have as an engineer. However, this unique property of JK flip-flop makes it unique because we can use this feature to create counters, and we'll see that in lecture number 19, how we can use JK flip-flop to create up counters, down counters, and up down counters, asynchronous, synchronous counters. Okay, now that we have the truth table ready, we're going to move on to the state characteristic table. And we know we use truth table to create characteristic table. In characteristic table, we also know that the inputs are basically the present states or the previous states, and right next to those are the inputs, which in this case are JK, and then we have the output, which is the next state. Okay, right, so for 3 inputs we have 8 possible combinations: 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Okay, here, now, when J is 0, and we're going to assume that clock is high, so when J and K both are 0, when J and K both are 0, what is the next state? Well, the next state is the previous state, and because the previous state is 0 here, so it will be 0. When J is 0, K is 1. When J is 0, K is 1. The next state is 0. J is 1, K is 0. J is 1, K is 0. Next state is, remember this Qn plus 1 is the next state. is 1, so we get 1 here. When j is 1, k is 1. When j is 1, k is 1. The next state is the complement of the previous state, and because the previous state is 0, so the next state is going to be the complement of the previous state, which is 1. Okay, 0 0 0 0 is a memory, so because it's 1, so we'll have 1 here. 0 1 0 1 0 1 0 1 0, output is 1, next state is 1, and then 1 1 1 1. The next state is actually the complement of the previous state. Because the previous state is 1, so this has to be 0. Okay, so this is our state table, also known as the characteristic table. We are now going to move on to the next sheet. We're going to work on the excitation table now. Before I work on the excitation table, I just want to quickly get an expression for qn plus 1, looking at this truth table. Okay, again we have this most significant bit qn here, and then jk as the inputs. Okay, so 0 here, 1 here, 2 3 4 5 6 and 7. Let's look at the min terms. We got 1 here, we got 1 here, got 1 here, and we got 1 here. I think most of you agree, well, we will go with this one right here, and then this pair right here at the bottom at the edges. Okay, let's get the equation for the next state. Qn plus 1 is actually going to be equals to q bar n dot j. Qn, this one right here, remember this is qn bar, this is qn, okay, and this is j bar, k bar, and this is jk bar, so the common is k bar, so we get k bar here. Okay, okay, similarly, if you wish, you can also get the expression for j and k. But before we get that expression, let's work on the excitation table. In excitation table, we know that we keep present state and next state right next to each other, and then followed by the inputs, which are j and k in this case. So 4 possible combinations: 0 0 0 1 1 0 1 1. Okay, when qn is 0, qn plus 1 is 0. When qn is 0, qn plus 1 is 0. Qn is 0, qn plus 1 is 0. Is there any other instance right here where qn and qn plus 1 are 0? No. So we got 2 of these. So look at j. J is 0 in both cases, so we put j 0. K is 0 and 1, so we put it as don't care, which means it could be 0 0 or 0 1. Similarly, we do it for 0 1. 0 1 and then 0 1 right here. So we got these two cases here. J is 1 in both cases, and here k is 0 and 1, so again don't care. Okay, moving on to 1 0. We have 1 0 here, and then we also have 1 0 here. 1 0 1 0. Okay, so k is 1 in both cases. K is 1. J changes 0 and 1, so it has to be don't care. And the last one, 1 1, which is actually this one right here. You got 1 here and 1 here, and this one right here. So you got 1 here and 1 here. So if you do look at these ones, you get k0 here and k0 here. So you get k0 here. And if you look at j is 0 here, j is 1 here. So it has to be don't care. Okay, so now that we have completed the excitation table, we can use this table to get an expression for j and k. Okay, so this is Qn, your most significant bit. You got Qn here, and you get Qn plus 1. Similarly, you got Qn here and Qn plus 1. Okay, so we look at J here first, this column. 0, 1, don't care, don't care. We'll go with this one right here, which would mean J is equals to Qn plus 1. Your next term is basically J, but this is what it means. Okay, for K, we look at this column right here. So we got X here, we got 1 here, and we got 0 here. So we will make this pair right here, which would mean K is equals to Qn plus 1 bar on the whole thing. Okay, so with this we have finished JK flip-flop. We saw it's very exciting in a way that when J and K both are high and the clock is high, the next state is basically the complement of the previous state, which makes it unique in a case that we can use that. We'll use that feature to create counters in lecture number 19. But what is wrong with JK flip-flop? The thing that is wrong with JK flip-flop, is because it is uncontrolled toggling. Okay. We also refer this to as logic race condition. Okay, this is the JK flip-flop. There's another kind of flip-flop which we know as a T flip-flop. So here's the T flip-flop right here. It's pretty much JK flip-flop, except for it has the input T, which is connected to both J and K, which basically means if T is 0, J is 0, K is 0. Okay, if T is 1, then J is 1 and K is 1. Okay, so this is more control. When we are setting the value for T equals to 1, that means we are actually going to toggle, because J is 1, K is 1, and we know what happens when J and K is 1. Toggling is a control action of toggling the bits going from 0 to 1, 1 to 0, and 0 to 1. We use T flip-flops for toggling. Here is the truth table right here for the T flip-flop. Okay, when clock is 0, you really don't care what T is. The next state is going to be the previous state. When clock is 1 and T is 0, which means J and K both are 0. So let's look at the truth table for the JK flip-flop that we just created. When J is 0, K is 0, the next state is actually the previous state. So the next state is going to be the previous state. So we have Qn here. So it's acting as a memory here again. When T is 1 and clock is high, with this, which means that J and K both are set to high. So again, looking at the truth table, when J and K both are high, you have the next state, which is the complement of the previous state. So you have Qn bar here. Okay. And then from this table, this is sort of like an excitation table also. You can get the Qn plus 1 equation here. So you got T bar Qn plus T Qn bar. So looking at the min terms, so this is what we know as a T flip-flop, and where the T here actually stands for toggling. So here's a quick summary of what we have done so far. We started with the SR latch using the NAND gate, and we saw how we use that NAND gate to create SR flip-flop. One of the issue with SR flip-flop was when S and R both are set to high, we had an undefined behavior. We got into a forbidden state where both the inputs were outputs were same, which cannot happen because Q and Q naught has to be a complement of each other. So it might store a 1, it might store a 0, or output might oscillate. So we are not really sure. To ensure that SR is not equals to 1 1, we can avoid that undefined behavior or forbidden state. So the designers, they use the D latch in combining a combination circuit to SR latch, making sure that inputs are not high at the same time, which was basically using an inverter. Which was basically using this combination circuit, this inverter, and then feeding it into the NAND gate, so making sure that S and R are not same at the same time. Then we did the JK flip-flop, which acts like an SR flip-flop basically, plus it has the third input. The outputs are fed into the input of the NAND gates, and that acts as a flip-flop. It toggles when J and K, or in other words S and R, both are set to high, which is an interesting feature. We get more control on this toggling effect with the T flip-flop. T flip-flop is basically JK flip-flop, plus we have one T that is connected to both J and K. So the output, the inputs at the JK can either be 0 0 or 1 1. And we know when JK is 0 0, it acts as a memory, and when it's 1 1, it basically toggles. So with a single input T that toggles the flip-flop when 1. Nearly all modern sequential circuits use D flip-flops. For the most part, we are going to use D flip-flops in this lecture series, and also JK flip-flop. Okay, so stay tuned for the next lecture, and I'll see you guys. Thank you for watching. Bye.